We're going to read through a paper today. This paper here, the semaglutide reduces cardiomyocyte size and cardiac mass in lean and obese mice. Mice, not men. I have all of the written details of this paper on my sites. So I have a lot of extra discussion there. There's a link to the paper, which is free online at the sites. The sites are wmbriggs.com or wmbriggs.substack.com. It's wmbriggs.substack.com or just plain.com. And it's a very short paper. You could read it easily, but I want to look at how we should read these papers as a matter of course. This is sort of to augment the class, and this is a typical research shows kind of a paper, and I want to look at how they present the evidence. It's a very simple study. They took a bunch of mice, not men, and they fed them a high-fat, high-sugar diet and fattened them up, and they all gained a bunch of weight. They took them off that diet for a period of time, and the mice lost some weight, but presumably not all of the weight. They only report on average, and I'm going to show you what I mean by that in a second. And then they fed the mice for another period of time, either regular mice chow, that's what they call it, also called a vehicle or control, just a regular feed. And then they gave a second half of the mice, they split the mice into two groups, the semaglutide in with the regular mix. And then they looked at the differences in the groups, not the per mice difference, in the groups, but just differences in the groups. And I want to talk about that just briefly. Now, they have everything crammed into one figure, and I have the highlights on the blog and the webpage and so forth. But let's look at some of these things here. The very first thing they looked at, just the one on the left, the picture here on the left is just an illustration of the protocol. Here is the body weight at the end of the period of time after they fattened them up, after they took them off the diet, and after they had been feeding them either the control or the semaglutide. Here's what we see. And this is the vehicle or the control group, if you like to say, and this is the semaglutide right here. And then they said there's a difference. Well, yes and no. We need to understand that the language that they use in the saying there was a difference between these two groups. Yes, there's lots of differences between these two groups. There's lots of them, and they're using a hypothesis testing sort of verbiage, and that's very unfortunate. The mean is indicated by the tops of these bars, and these other bars here are kind of a standard deviation difference or standard error difference of that mean. It's not interesting to us. What is interesting is this. Here's 3 mice right here in the control group or the vehicle group who have a body weight in grams of about, 28 or so. They have a higher body weight than several, or at least tied with, several of the mice who were on the semaglutide. So it's not that every mouse had who ingested this stuff did better in the sense of having a lower body weight than the mice who were on the vehicle. Although the mice who were on the control group, they had a lot more who were a lot higher. And in the semaglutide group, they had some who were indeed lower. And there's not much dispute that on average, in some people, this is the way to say it in people, some people will lose weight, they'll lose body mass. And the mass can be in fat and the mass can be in muscle. And that's the concern in this paper, or the concern in you if you're taking these drugs. Like, I won't mention the names because I'll get dinged by YouTube. So you know the names of these drugs if you could look on my website and everything, and I have them. So this gives us, ignoring all these asterisks and all these nonsense hypothesis testing verbiage, we could see there are differences in body mass. But here's the problem: we don't know what the mice look like before the start of the trial. They fed them this high-fat, high-sugar diet, and they said it was specifically designed not to affect the mice's cardiac output or their hearts in any way. Well, is that true? We don't know. We don't know. They said that that was the design of this thing, but we don't know whether or not it's true. What they should have did is they should have did something like this in this stunningly beautiful graphic here. Here's a times 0, and this could be anything. This could be the body mass. This could be, we're going to look at something called ejection fraction, and a bunch of other stuff. This could be on this axis here, whatever the axis of measurement of importance is. And here is at the end of the fat. I call it fat. That's an FA2. Here is at the end of the fat period, after the period of time in which they've been feeding them the high fat, high sugar diet. And here is at the end. So presumably a mouse started here, just to give you an idea, maybe in body fat, and then he went up a bit as they've been feeding him this stuff, and then he lost some weight, and even maybe more weight than he started with before on this thing. We don't know. We don't have a natural control group of each mouse with itself. And there's a danger of looking at just averages, because some of these body masses here, were these three here the mice who started low, and now we're just seeing them low? We don't know. And so that gives, it's not that it's wrong. It's not that this is wrong, but it should give us some pause and give us some idea that there's uncertainty in these results that's not accounted for in the way they wrote about it. So we immediately ask, why didn't they draw a graph like this? They could have used two different colors here. I've stunningly used a light blue and a blue because I couldn't figure out how to change the marker color on this thing to indicate the vehicle and the drug group. And they could have done something like this, and we would have seen all of them in time and seeing what was going on. Okay. Now that criticism applies to just about every single graph that they have. So I'm going to ignore that criticism, but you have to understand it's there the whole time. Okay, so here's the fat mass measured on each mouse relative to the tibia length. And that's a sensible thing to do because, of course, why didn't they do the body weight by the tibia length, you wonder too? Because, of course, bigger mice are going to have bigger body weight, and they may have more fat mass, not because they're fatter, just because they're bigger. So some kind of normalization makes sense, which they did here. And it's, again, we have that same problem. We don't know who started where and so forth. But as you can see, the fat mass, there's only one or two mice here out of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We only got 10 mice. 2 of them did about the same as, or no worse than any of the semaglutide mice. And one of these mice did worse than, the semaglutide mice did worse than the vehicle mice. So not every mouse is benefiting from this, all right? So that's neither here nor there. These are kind of baseline, not baseline, but these are kind of figures that are not unexpected given that weight loss has been seen in mice and in humans. Okay, now here's the first important graph. And they say no difference was seen in ejection fraction between the mice in the vehicle and the mice in the semaglutide groups. This is a bizarre way of speaking. It's not English. Of course, there are differences. Look at them. Here's a bunch of dots over here, and here's a bunch of squares over here. There are differences, but they mean in a hypothesis testing, it wasn't significant. So they say there was no difference. Well, that's rot. There are differences. In fact, it's quite clear. The mice in the semaglutide group have higher ejection fraction. Now, what's ejection fraction? It's the amount of stuff that's squeezed out. You want to be able to squeeze out, every time your heart squeezes, you want it to squeeze out the available blood, okay? And that's good. Higher ejection fraction up to a point is good. Up to a point. In humans, it's about 70-75%. Above that, your heart's probably overactive. But low ejection fraction means you're not clearing out all the blood. Some of that blood's just sitting in there when your heart's pumping. It means your heart's not that efficient. And that could cause all kinds of other problems and so forth. Here they said there was no difference. But here it looks like there was a definite improvement in ejection fraction for at least some of these mice. But again, we don't see where they started at. We didn't see them at their baseline before they were doing things. Another criticism is this is all done by echocardiograph, these points right here. So this dot is measured at, I don't know what this is. What do you think? 65, something like this, percent. Now that's as a result of a scan, and which means there's some plus or minus attached to this. There's some uncertainty in each of these dots and each of these squares, but we don't see it. They didn't convey that to us. And the problem is the mice weren't blinded to the people, if they were, they didn't say, to the people making the measurements. And there's nobody easier to fool than a scientist doing his own research. Like I say, and I say it over and over and over again, every scientist believes a confirmation bias exists, but every single one of them believes it's for the other guy, never for himself. So there's some difficulty here. Are we really seeing what we're seeing? You know, what's the fuzz on all this? And again, this is where we really want, these are the main outcomes, things like ejection fraction, and the next one we'll see here in a second. These are the main outcomes. We really wanted to see where these mice started from and how the high-fat diet affected them, and then, how the high-sugar diet affected them, and then how the drug affected them. Okay, here is another type of measure. This is the ejection fraction is kind of like the systolic, you know, how your heart pumps and squeezes and then releases. And this is a measure of the diastolic, of the pressure as your heart relaxes. And again, they say there's no difference, but of course there are differences. There's differences between these dots here and these squares here, but there doesn't seem to be a lot of differences. So that may or may not be important. You tell me. Now here's the left ventricle mass. This is the main one. This is where the heart muscle, the squeezers reside. And here, it does look like they have 1, 2, 3, 4 mice, maybe 5, maybe 6, maybe 7 mice that had lower LV mass at the end of the time of their being on semaglutide. And some of them had about the same as the lowest mice in the vehicle group. When they're doing these tests, they're doing the test against the mean. So when you see that, when you read this headline or you read something about this, that the drug lowered heart mass or something like this, yes, maybe in all, maybe in some, probably in a few. It doesn't necessarily mean every single mouse who's got the drug had their LV mass lower. So that's how we need to read these things. But it does seem to indicate, as long as we assume that every mouse was about the same at the beginning and at the end of the high-fat, high-sugar diet, and now here, it looks somewhat damning for the semaglutide. Now, I don't know, I'm no expert in mice physiology, so I don't know the amount they fed them. You can read the paper, you tell me. Was it too much, too little? That's something I can't tell. And this again here is the heart weight, again relative to the tibia length. And we see here, this is the entire heart. And again, we have 1, 2, 3, maybe 3 mice in the drug group who had lower heart weights, normalized heart weights. But look at the top. The top seems to be all about the same. Maybe there's one or maybe one mouse in the vehicle group had a heavier heart weight. So it's not like it's a simple mean versus mean comparison here. There's more going on, and when we have these crummy hypothesis tests, we lose a little bit of information. One problem is the way they convey this information, and I'll show you here. That's this one here. They do the cardiomyocyte area. The myocytes, the myocardium, those are where the cells are that do the squeezing, the contracting. And so here they measure this with some electronic means. It's not important to us. And they have a lot of measures over here, and they're all in the form of these dots. And it kind of looks like there's less area in the mice with fed semaglutide, and they do indicate that means are lower and so forth. But the problem with this is, you know, you can't really tell. Your eyes are no good at judging these kinds of differences. Eyes are no good at conveying differences. Basically, it would be better if we had like a histogram comparison. Here's the one group, maybe the semaglutide group, and then here's the other group, and all this would be like a histogram, and this would be, what was it, the myocyte area, something like this. So if we had pictures of this, just histograms side by side, it would be a lot easier to tell what's going on. And you see that there's only a couple that are larger out of all these measures. I don't know how many measures they did on each mouse. So the next thing they did was, all right, well, maybe something's going on in each mice. Maybe some genes that are known to be, whatever this means, known to be associated with heart problems and so forth, or with fibrosis, are expressing themselves, and what's the level of their expression in each of these mice and stuff. And they again say there's no differences. There's no differences. But of course we can clearly see there are differences. Here in this first MAC2 gene, all of the large values, the very large values, are all in the semaglutide group. All of the large values are in the F480 group. All of the large values are in the post-N group, and so on. And that's the same for, and they also looked at atrophy, the same kind of groups, but there's more even spread between the dots here. But this is a difference. It doesn't mean that the mean's not different. The means can be the same, but the spread of these distributions can be different. So this is a very big danger of this hypothesis testing language. It would have been far better not to give any of this stuff, not to use those kind of words, and just give us words. Here's what happened. So in order to show maybe there was something wasn't going on, they did the same kind of experiment again. They just fed just in regular mice, not the ones that they had fattened up in lean mice. The same kinds of thing, the same two groups. And now here the expression levels are sort of inverted. The high ones are all in the I should explain about fibrosis. Fibrosis is so when you have damaged tissue, like you have the damage in the myocardium, it'll be replaced by this. It'll be quickly replaced, maybe tissue that's not the same as the squeezing muscles, and just like you can think of it like fibers, I guess. And it won't be effective tissue. So a damaged heart can repair itself, but it'll still be inefficient at the end. So, but the point of my point here is, in the lean mice, the ones that they never fattened up, we had a reverse. Up here, all the very high values were in the semaglutide group, and here, all of the high values, or most of them, are in the natural group. It would have been far better to say things like, just drawing a picture. It would have been far better to use the natural control group of each mouth with itself, and then we could have talked about relative changes. We wouldn't have to do this tibia link nonsense, because it's not a perfect measure, because a mouse can be smaller, but for whatever reason has a longer or shorter tibia than on average, and so we're not getting a clear picture. Why not just use the mouse as its own control group, or its own reference group, I should say, as time goes on? So we have a lot of stuff. Oh, here, and they had, in the last one, they had that same thing. Here's the human cardiomyocyte area. And these are human cells that are more, you can think of it, kept in a petri dish. These are immortal cells that they've kept alive, and they just juiced with semaglutide. Now, that's not going to happen in real life. You're not going to go in there and inject. Well, some of it might get to your heart. I don't know. You guys who are physiologists can tell me. But when you're getting these injections, I don't know how much it makes it to the heart, and how much is assimilated in other areas of the body before it gets there. But they did try this in tissues, and this is human cells. And it does look, and this is the problem. We got these blobs again. It's really kind of hard to tell what's going on. But look at this right here. The human cardiomyocyte area here is lower. The lowest values are in the control, and the highest values are in the highest value is in the semaglutide sample. So showing a picture like I did here would have been some kind of histogram where you're showing this side by side. We can get a full picture of what happened. Remember, we don't need hypothesis tests to tell us what happened. We can look at the data and see what happened. If we're trying to infer like they're asking us to, like the LV mass or the heart rate is lower because of semaglutide, that's something we're doing extra to the data. The hypothesis test can't say anything about that. We don't know anything about cause from any kind of statistical test we can do. We bring cause to the data. We infer the cause from this. If we say there's no other causes and we say there's nothing important about differences in the beginning values or the middle values of any of the mice, and all the tibia links are the same, and there's no other genetic differences, and blah blah blah, why then we could say the only cause left over is semaglutide. So there's what you really want to know is, who cares about mice? Mice are not going to be being fed or being injected with semaglutide on any kind of regular basis. You want to know what's going to happen to you. There have been other reports in the paper, links, or rather I should say cites, other studies that do show, in this step 1 trial, I guess they called it right here, the semaglutide treatment effect in people with obesity clinical trial, there was some evidence of lean muscle mass. So if you want to know what's going to happen to you, you can learn some things possibly by looking at this study, but not everything. There's a lot more uncertainty in the results when you try to read this kind of stuff carefully, rather than looking at just headlines. Now, I did this in class on Monday, class 30, hypothesis testing stinks, to look at a research paper shows and try to think about other things that can explain the data. That's always a scientist's duty, to try to come up with any other explanations than the only ones that he was trying to sell you. But most scientists are very bad at this anymore. Good scientists, great scientists are good at this, and so they don't do such a good job here, but maybe they didn't have to. You have to judge this for yourself. All right, that's it. Again, go to wmbriggs.com or wmbriggs.substack.com. You get all the links and the full discussion. Thanks very much for listening.